Welcome to This Explainer. You know, right now, as you're just sitting there, billions of microscopic chemical engines are firing all at once. And they're doing this just to keep you alive and to keep the world turning. We walk through our daily lives totally surrounded by these constant transformations, materials changing their state, organic matter breaking down, massive steel structures weakening, and honestly, we rarely stop to appreciate the intricate molecular mechanics making the whole shebang happen. Well, today, we're pulling back the curtain to reveal exactly how the core types of chemical reactions work, but we're going way beyond just the basic textbook definitions. We're going to look at the profound, cascading effects these reactions have on both our natural ecosystems and the synthetic, built environments we live in. Get ready to see the invisible forces shaping our world in a completely different way.
Okay, let's dive into this with a question that, at first glance, might seem a little out there. What on earth connects a discarded, rusty nail you might find lying in the back of your garage to the human breath you literally just exhaled? They seem like they belong to completely different parts of our daily experience, right? Yet they actually share a profound underlying connection. They are both the direct result of oxidation. Whether it's a piece of iron surrendering its electrons to the atmosphere, or your own cells breaking down glucose to power your body, these aren't just random events. They're highly specific chemical reactions unfolding right in front of us. It's not magic, it's molecular science hard at work.
So here is our structural roadmap for the explainer today. First, chemistry in plain sight. Second, the 4 core reactions. Third, impacts on natural environments. Fourth, chemistry in built environments. And finally, staying safe and responsible.
All right, let's get into section 1, chemistry in plain sight.
It's time to take chemistry out of the sterile laboratory and put it exactly where it belongs, right in our own backyards and kitchens. Think about the stuff we might casually call everyday magic. You strike a match and wood burns. You plant a tiny seed and this incredibly complex green organism grows. You leave leftovers in the fridge a few days too long and suddenly you've got spoiled food. Now, these aren't just random accidents. They're highly specific, structured chemical changes. At a fundamental level, a chemical reaction is really just about breaking existing molecular bonds and reforming them into entirely new configurations. And this process often requires what we call activation energy. Think of it as a thermodynamic spark, like striking that match to kickstart the whole transformation. So whether you're observing a color shift, watching gas bubbles form, or feeling heat radiate off a fire, you are witnessing atomic bonds breaking and reforming in real time.
Moving right along to section 2, the 4 core reactions.
Our first core reaction is absolutely crucial to human history. We're talking about combustion. Simply put, combustion happens when a substance reacts super rapidly with oxygen. Crucially, this is a highly exothermic reaction, which just means it releases significantly more energy than it consumes, and it blasts out that excess energy in the form of heat and light. Oxygen is the absolute baseline requirement here. Without it, acting as an oxidizer, this rapid energy release simply cannot happen. So whenever you think of combustion, you're thinking of the fundamental chemical engine that has literally driven human progress, provided warmth, and illuminated our environments for millennia.
And this brilliantly illustrates exactly how this scientific definition applies to familiar things. Think about burning wood to cook a meal, or turning on your stove to use LPG gas, or even just lighting a candle during a power outage. In every single one of these scenarios, the complex hydrocarbons within the fuel source are being violently broken down by the oxygen in the air around it. They aren't just magically disappearing, they are rapidly recombining to form entirely new byproducts, mostly carbon dioxide and water vapor, all while releasing that massive burst of exothermic energy we were just talking about.
Our second core reaction is decomposition. If you think of a lot of chemical processes as building complex structures, well, decomposition is the great dismantler. This happens when one complex compound breaks down into 2 or more simpler substances. It's really the perfect microscopic expression of entropy. The universe fundamentally favors a state of disorder, and decomposition is exactly that. Complex, highly ordered molecular structures inevitably returning to simpler, higher entropy states over time. It's basically a systematic dismantling of complexity, straight back into foundational building blocks.
The absolute most visceral way to see this entropy in action is just to look at our agriculture in our kitchens. When you open your fridge and find food that's spoiled, you're watching complex organic molecules break apart.
But, this breakdown is absolutely essential for life on Earth. Just think about the process of composting organic matter in a garden. The decomposition reaction takes dead leaves and fruit peels and breaks them all down into nutrient-rich soil. More specifically, microbial decomposition drives the nitrogen cycle. It unlocks trapped nitrogen in decaying matter and converts it into ammonia and nitrates, setting the stage so that a brand new generation of plants can absorb it and grow.
Okay, moving on to the third type, single replacement. You can kind of think of this like a dance floor, where a third person cuts in and replaces one of the partners, leaving the displaced partner on the sidelines. In chemistry, this happens when one element steps in and replaces another element within a compound. But the crucial underlying science here is governed by what we call the reactivity series. This chemical tap-out doesn't just happen randomly. The replacement only occurs if the new incoming element is intrinsically more chemically reactive than the one it's trying to replace. If it isn't, absolutely nothing happens. No reaction at all.
So where do we actually see this whole reactivity series playing out? We see it all the time in industrial work, metalworking, or heavy-duty cleaning where metals are reacting with acids. Let's look at a concrete example. If you drop a piece of solid zinc into a solution of hydrochloric acid, a rapid single replacement reaction occurs right before your eyes. Because zinc is higher up on the reactivity series than hydrogen, it aggressively kicks the hydrogen out of the compound. This forms aqueous zinc chloride and releases pure hydrogen gas in the form of rapid bubbling. It's a pretty aggressive, invisible swap, happening entirely at the atomic level.
Our fourth and final core reaction for today is double replacement. If single replacement is one partner cutting in, well, double replacement is two couples completely swapping partners to form entirely new pairs. In scientific terms, these reactions typically happen in aqueous solutions, where ions are free to just mingle and interact. When these ionic compounds cross paths, they can swap their positively and negatively charged components. The result is often the creation of a precipitate, which is a brand new insoluble solid that suddenly drops right out of the liquid, or a neutralization reaction, where the extreme properties of the original compounds are completely nullified.
Now, what's really interesting about this is how a classic, totally familiar reaction perfectly demonstrates some pretty advanced chemistry. If you ever mixed vinegar and baking soda to make a little papier-mâché volcano erupt, you orchestrated a rapid double replacement reaction. But let's look past the foamy eruption to the mature chemistry that's actually happening. The acetic acid in the vinegar and the sodium bicarbonate swap chemical partners to form carbonic acid. This is an acid-base neutralization. But it doesn't stop there. That new carbonic acid is highly unstable, and it immediately triggers a decomposition reaction, rapidly breaking down into water and carbon dioxide gas. That CO2 gas expansion is exactly what causes the explosive bubbling, elegantly connecting double replacement and decomposition in one single awesome event.
All right, let's pull back and look at the big picture in Section 3, Impacts on Natural Environments.
Nature absolutely relies on a really delicate, continuous balance of these exact chemical reactions. Let's look at the sheer biological symmetry between two of the most crucial ones, photosynthesis and respiration. Plants use a chemical reaction to take sunlight, water, and carbon dioxide to manufacture their own food, and they release oxygen as a byproduct. Then there's cellular respiration happening inside our own bodies. We breathe in that oxygen and react it with the glucose from the food we eat to generate kinetic energy, breathing out carbon dioxide. They are effectively the exact reverse chemical reactions of one another. The chemical outputs of the plant are the biological inputs for the human, and vice versa. It creates this perfectly balanced thermodynamic loop that sustains entire ecosystems.
Let's pivot to Section 4, Chemistry in Built Environments. There's this really fascinating duality to these reactions when we apply them to human civilization. Out in nature, we've got those incredible life-giving loops, like photosynthesis. But in our built environments, these exact same chemical principles pose massive threats. Take metal corrosion. Rust isn't just an eyesore on an old car, it is an insidious oxidation reaction that is slowly eating away at the structural integrity of our bridges, our pipelines, and our power grids. In fact, to put it in perspective, the economic impact of this single chemical reaction is staggering, literally costing the global economy trillions of dollars every single year in maintenance and infrastructure replacement. The reaction itself is just impartially following the laws of thermodynamics, but the consequences change drastically depending on the setting. Let's walk through this sort of mental cheat sheet to see how this builds into a cohesive understanding across different domains. When we map these reactions out, a remarkably clear picture emerges. The exact same exothermic combustion that perfectly cooks our food can, when scaled up in car engines and massive industrial factories, result in severe atmospheric pollution.
The acidic reactions that are so useful in metallurgy are the exact same chemical forces causing devastating corrosion on urban infrastructure. And conversely, these core molecular interactions in nature result in life-sustaining growth. It's the same fundamental chemical rules, but with vastly different macro-level outcomes depending entirely on our context and how well we control them.
Which brings us to our final part, Section 5, staying safe and responsible.
So, the crucial point is that understanding all these reactions goes way beyond just passing a chemistry test. It actually empowers us to manage our lives safely. Let's talk about household chemicals for a second. By knowing that seemingly harmless everyday cleaners can undergo dangerous double replacement and decomposition reactions, we understand exactly why we must absolutely never mix random supplies. Mixing common household bleach with ammonia, for instance, triggers a rapid chemical reaction that produces toxic chloramine gas. Recognizing that these molecular combinations have severe, immediate consequences proves why this scientific awareness is quite literally a matter of life and death. It guides responsible action in our homes and our communities.
Applying this knowledge on a daily basis doesn't mean you need to walk around in a lab coat. It just takes a tiny shift in perspective. The next time you see rust forming on a valuable tool, recognize it for what it is, an oxidation reaction. And know that applying a simple physical barrier, like a coat of paint, stops that chemical exchange of electrons dead in its tracks. When you're putting away your groceries, realize you are actively fighting decomposition, using temperature control via refrigeration to drastically slow down the kinetic energy of those chemical breakdowns. You literally have the power to observe the microscopic world acting on the macroscopic one, identify the core reaction at play, and take protective action to control your environment.
I want to leave you with a provocative thought to end our explainer today. Look away from the screen for just a second. Seriously, look around the room you're sitting in right now. What is one invisible chemical reaction happening in your immediate vicinity? Is it the cellular respiration actively happening in your own lungs to keep your brain focused on this? Is it a piece of fruit on your counter slowly surrendering to entropy and decomposing? Or maybe the battery in your phone undergoing a controlled chemical reaction just to power your device? Chemistry isn't just trapped in textbooks. It is the active, breathing, perpetually transforming world all around us. Keep observing, keep questioning, and use this knowledge to safely and smartly navigate your world. Thank you so much for joining me to explore these chemical mechanics, and I will catch you in the next explainer.